More than 60 million years ago, the largest flying animals in Earth's history were already established across coastal plains and inland seas. They did not move like modern birds. Their wings stretched across distances that would exceed small aircraft, yet they relied on air currents rather than constant motion. Much of their time in the sky was spent gliding, covering ground without effort. From below, there was no consistent signal of approach. Movement above did not always produce sound. What reached the ground first was often a shifting shadow, brief and difficult to interpret. Life on land adapted to this condition. Small dinosaurs, early mammals, and reptiles occupied environments where overhead space could not be ignored. Open terrain offered visibility, but it also removed protection. Forest edges, riverbanks, and floodplains became places where awareness extended upward as much as outward. Some species developed wider fields of vision. Others responded quickly to changes in light rather than shape. These were not precise detections, but fast reactions to interruption. The sky itself was not empty. It carried movement that did not follow predictable paths. Large bodies could appear, circle, and disappear again without remaining in view for long. Presence was intermittent, not constant. Some of these animals stood as tall as a giraffe when on the ground, yet they could still launch into the air. This creates a structural problem. Large mass usually limits flight, requiring energy that scales beyond what muscle alone can support. Yet fossil evidence confirms repeated success across different environments and time periods. Tonight, we focus on how the sky became a functional layer of the environment, shaping survival on the ground, and how large flying reptiles maintained controlled flight at an extreme scale under the physical limits of their world. But before we begin, I'm curious where you're listening from and what time it is for you right now. It's always fascinating to see how far these moments travel, and if you'd like to support the channel, a like and subscribing truly helps it grow. Now, let's continue. The ground itself did not hold the same shape it does now. Its edges spread differently, its boundaries softened by water that reached far beyond familiar limits. During the late Cretaceous, the continents were not arranged into the distinct forms seen today, but existed as drifting masses, still in the long process of separation. Vast portions of land remained connected or only partially divided, and between them, shallow seas expanded inward, covering regions that would one day stand as dry ground. What appears stable in the present was, in that time, still in motion, guided by forces too slow to notice in a single lifetime, yet powerful enough to redraw the world over millions of years. Water played a quiet but dominant role in shaping this landscape. Sea levels stood much higher than they do now, not because of sudden flooding, but due to a warmer planet where ice at the poles was minimal or absent. Without large ice sheets to store water, the oceans spread outward, filling low-lying regions and forming broad inland seas that divided continents into smaller land masses. One such sea stretched across what is now North America, creating a long, shallow corridor that connected distant coasts. These waters were not empty expanses, but rich environments filled with marine life, their surfaces reflecting a sky that carried movement above and currents below. Along the edges of these seas, coastlines shifted gradually, forming wide plains where land and water met without sharp distinction. Sediment carried by rivers settled into these regions, building floodplains that stretched for great distances. These areas supported dense vegetation, nourished by consistent warmth and moisture. Forests grew thick in some regions, with towering plants adapted to a climate that rarely experienced cold. In other areas, the land opened into broader spaces where vegetation spread lower and more sparsely, shaped by differences in rainfall and soil. The climate itself moved with a steadiness that defined daily life. Temperatures remained generally warm across the globe, reducing the contrast between equatorial and polar regions. Seasonal changes existed, but they were less extreme, allowing ecosystems to remain active throughout the year. Rainfall patterns varied depending on geography, with some regions receiving frequent moisture, while others experienced longer dry intervals. These patterns influenced not only the plants that could grow, but also the animals that depended on them, guiding where different species could survive and thrive. Air and water together created pathways that extended beyond the ground. Warm temperatures encouraged the formation of steady wind currents, and these currents moved across open landscapes and coastal regions with a reliability that could be felt even at the surface. In areas near inland seas, rising air from heated water created gentle upward flows, invisible yet consistent, shaping movement both above and below. The environment was not divided into separate layers, but functioned as a connected system where land, water, and air continuously influenced one another. Compared to the present, the world carried fewer sharp contrasts. Ice was rare, coastlines were broader, and the separation between ecosystems was less defined. Movement across regions could occur more gradually, allowing species to expand or shift their range in response to subtle changes in climate. Distribution was not random, but closely tied to temperature, moisture, and the presence of water, forming patterns that stretched across continents and seas alike. Within this arrangement, life found its place, not in isolation, but as part of a landscape that was constantly shaping and being shaped in return. Movement at ground level rarely settled into stillness, even in moments that appeared calm from a distance. Beneath the broad stretches of vegetation and across open surfaces where cover thinned, life unfolded in brief intervals, shaped by caution and the need to respond without delay. Small dinosaurs moved with measured steps, their bodies held in a balance between motion and restraint, while early mammals remained closer to the edges, emerging and retreating with a rhythm guided by instinct rather than routine. Reptiles, adapted to warmth and stillness, occupied spaces where heat gathered, yet even they remained alert to shifts that passed across the surface around them. The scale of these animals influenced how they experienced the world. Smaller bodies required constant intake of energy, and this demand drew them outward into spaces where food could be found, even when those spaces offered little protection. In open environments, distance could not be relied upon as a barrier, and visibility extended in all directions without obstruction. The ground itself held few places to disappear completely, and so survival depended less on strength and more on the ability to remain unnoticed. Patterns of coloration, subtle shifts in posture, and careful timing allowed some to blend into their surroundings, becoming part of the textures that surrounded them. Awareness became a continuous state rather than a response to immediate danger. Heads turned in small increments, eyes scanning not just what lay ahead, but the spaces between movement, reading changes in light and motion that passed quickly across the surface. Reactions needed to be immediate and precise, as hesitation reduced the margin between safety and loss. Muscles remained prepared for sudden bursts of speed, and these movements were often brief, directed toward the nearest form of cover, whether it was a cluster of plants, uneven terrain, or a narrow opening in the ground. Shelter, when it existed, was often temporary. Dense vegetation provided some concealment, though it could also restrict visibility, creating a balance between hiding and awareness that had to be constantly adjusted. Burrows offered more secure refuge for certain species, particularly early mammals, whose smaller size allowed them to retreat beneath the surface. These underground spaces moderated temperature and reduced exposure, forming stable environments within a landscape that was otherwise open and shifting. Still, time spent below ground limited access to food, and so emergence was inevitable, returning each individual to the same conditions of exposure. Daily life followed patterns shaped by these constraints, periods of activity aligned with moments when risk could be managed, though not eliminated. Feeding, movement, and rest were all influenced by the surrounding environment, and each action carried a degree of calculation that was not conscious but deeply embedded in behavior. The presence of others added complexity, as groups could offer increased detection of change, yet also drew attention through movement and sound. Some species remained solitary, relying on silence and stillness, while others accepted the trade offs that came with living in proximity. Across this landscape, survival did not depend on a single adaptation, but on a combination of traits that worked together in subtle ways. Speed, perception, concealment, and timing formed a system that allowed these animals to exist within an environment where exposure was constant and protection was limited. The ground held life in motion, never entirely at rest, shaped by pressures that were present in every moment, whether visible or not. Long before the largest forms traced wide arcs across the sky, smaller shapes moved through the air with a kind of cautious precision, testing a space that had not yet been fully occupied. These early flyers belonged to a group now known as pterosaurs, a lineage distinct from dinosaurs, though emerging alongside them within the broader family of reptiles. Their presence marked one of the earliest successful experiments in powered flight among vertebrates. Appearing more than 200 million years ago, during a time when life on land was still reorganizing after earlier upheavals, their bodies carried a structure unlike anything that would come later. Instead of feathers, they bore wings formed from a thin membrane of skin and muscle, stretched along an elongated fourth finger that extended far beyond the others. This design created a surface capable of interacting with air in a controlled way, allowing lift to form beneath them as they moved forward. Their bones were light, filled with air spaces that reduced weight without sacrificing strength, and their joints allowed a range of motion suited for both flight and movement on the ground. Even in these early stages, the foundation for sustained aerial life had already taken shape. At first, their size remained modest. Many of the earliest pterosaurs were no larger than modern birds, their wingspans limited, their bodies adapted for agility rather than scale. They likely moved between trees, cliffs, and open clearings, using short bursts of flapping combined with gliding to navigate their surroundings. Their flight was active, requiring regular movement of the wings to maintain height, and their time in the air was closely tied to the need to feed or relocate. These smaller forms existed within a world where the sky was not yet dominated by giants, leaving space for gradual refinement and expansion. Over time, subtle changes accumulated across generations. Variations in wing shape, muscle strength, and skeletal proportions allowed some species to travel more efficiently, reducing the energy required to remain airborne. As these traits became more pronounced, certain pterosaurs began to grow larger. Their increased size, supported by improvements in flight mechanics and environmental conditions that favored their expansion. Warmer climates and stable air currents provided opportunities for longer periods of soaring, and the absence of competing aerial vertebrates allowed these reptiles to explore ecological roles that remained largely unfilled. This progression did not occur suddenly, but through a steady widening of possibility. Larger wings allowed for greater lift, which in turn supported heavier bodies, and with increased size came the ability to travel farther distances while expending less energy per unit of movement. Their interaction with the air shifted gradually from constant effort to a more balanced exchange, where motion could be sustained with minimal exertion under the right conditions. The sky, once navigated in brief intervals, became a space that could be occupied for extended periods, opening new pathways across landscapes that were otherwise difficult to traverse. Despite their growing presence above, these animals retained strong connections to the ground. Their limbs allowed them to walk and launch with coordination, and their lives remained tied to places where they could rest, feed, and reproduce. The development of flight did not remove them from the terrestrial world, but extended their reach within it, linking distant regions through movement that bypassed obstacles below. Across millions of years, this group continued to diversify, their forms adapting to different environments and ways of life. From modest beginnings, they expanded into a range of sizes and behaviors, gradually establishing themselves as the first true masters of the sky, not through sudden dominance, but through a long, quiet process of refinement and change. Flight in these early reptiles did not begin as a perfected system, but as a gradual coordination of structures that, over time, learned to work together with increasing precision. Their bodies carried a framework that allowed the air itself to become something they could lean against, not through feathers, but through a continuous surface of skin that stretched outward from the body. This membrane extended along an elongated fourth finger, a single digit that grew far beyond the others and acted as the leading support for the wing. From that point, the membrane connected back toward the body and hind limbs, forming a broad, flexible surface that could change shape in response to movement. This design created a wing that behaved differently from those seen in later flyers. Rather than a rigid surface divided into layered structures, it remained responsive, capable of subtle adjustments as air flowed across it. Muscles embedded within the membrane allowed fine control, altering tension and curvature in ways that influenced lift and stability. The wing was not a fixed tool, but a dynamic extension of the body, shaped moment by moment to match the conditions of the air. This flexibility allowed early pterosaurs to experiment with different styles of movement, gradually refining how they generated and maintained lift. Beneath the surface, their skeleton supported the demands of flight through a balance of strength and lightness. Bones were hollowed by internal air spaces, reducing overall weight while preserving the rigidity needed to withstand forces encountered during movement. This internal structure allowed their bodies to remain relatively large without becoming too heavy to leave the ground. The arrangement of these bones also contributed to balance, distributing mass in a way that supported controlled motion both in the air and during moments of contact with the ground. At the center of this system, the chest played a crucial role in initiating flight. Strong muscles anchored to a pronounced sternum provided the force needed to begin movement upward. Launching was not a simple upward push, but a coordinated action involving both the forelimbs and hind limbs, working together to generate enough power to lift the body into the air. Once airborne, these muscles continued to operate, though their role shifted depending on the style of flight being used. Unlike birds, whose wings are formed from modified forelimbs with feathers creating lift through a series of overlapping surfaces, pterosaurs relied on a single extended structure. This difference shaped how they interacted with the air. Their wings allowed for a wide range of motion, but required careful control to maintain stability. The absence of feathers meant that airflow behaved differently across their surfaces, and their flight depended more heavily on adjusting the shape and angle of the membrane in response to changing conditions. As these adaptations became more refined, the energy required to remain airborne began to decrease. Instead of relying solely on constant flapping, Many pterosaurs developed the ability to glide for extended periods, using rising air currents to sustain height with minimal effort. This shift allowed them to travel greater distances without exhausting their energy reserves, transforming flight from a short term activity into a sustained mode of movement. The interaction between body structure and environmental conditions created a system where efficiency emerged naturally, shaped by both anatomy and the invisible patterns of the air through which they moved. Through this gradual alignment of form and function, flight in pterosaurs became not just possible, but sustainable, opening a space above the ground that could be occupied with increasing ease and precision. Size did not arrive all at once, but unfolded slowly, almost imperceptibly, across generations that stretched far beyond any single moment. What began as modest forms moving through the air gradually extended outward, each variation building upon the last, until wings widened and bodies followed, supported by structures that had already learned how to carry them. The transition toward larger proportions was not a sudden leap, but a steady adjustment, guided by subtle advantages that accumulated over time. As wings grew broader, the relationship between body and air began to shift. Larger surfaces interacted more efficiently with rising currents, allowing lift to be maintained with less continuous effort. This change altered how movement through the sky was sustained, reducing the need for constant exertion and opening the possibility of longer, more controlled travel. With each increase in wingspan, the balance between weight and support became more refined, enabling bodies to expand without losing the ability to remain airborne. The environment itself played a quiet but essential role in this progression. Warm conditions across much of the planet encouraged the formation of stable air patterns, where heated surfaces caused air to rise in slow, predictable flows. These upward currents provided natural support, allowing large wings to capture and ride them with minimal movement. In regions where land met water, temperature differences created additional layers of air motion, further enhancing the ability to stay aloft. The sky was not uniform, but filled with structures that could be used by those adapted to recognize and utilize them. At the same time, the aerial space remained relatively open. Few other vertebrates occupied this domain in a comparable way, leaving a wide range of ecological roles unfilled. Without significant competition, pterosaurs were able to explore different strategies of movement and feeding, gradually expanding their presence across various environments. This absence of direct rivals allowed size to increase without immediate limitation, as there were few constraints on how large a flying animal could become within the available niches. As these conditions persisted, larger forms became more common. Their increased scale offered advantages beyond flight efficiency. With greater wingspans, they could travel across broader regions, observing and accessing areas that smaller animals could not easily reach. Their presence extended over coastlines, plains, and inland regions, connecting distant parts of the landscape through movement that required little direct interaction with the ground. This ability to move freely across large distances reinforced their role within the environment, allowing them to occupy positions that were difficult for other species to challenge. Dominance in the sky did not emerge through direct conflict, but through a gradual filling of space. As larger pterosaurs became more efficient and widespread, they began to define the structure of aerial life. Smaller forms either adapted to different roles or remained within more limited ranges, while the largest individuals continued to expand their reach. The sky, once only briefly occupied, became a continuous environment shaped by their presence. This process unfolded without sharp boundaries or sudden changes. Instead, it reflected a steady alignment between anatomy and environment, where increasing size was supported by conditions that made such growth possible. Over time, the result was a range of flying reptiles whose scale redefined what the air could hold, transforming the sky into a domain where size itself became an advantage, sustained not by force, but by the quiet consistency of the world around them. Among the many forms that came to occupy the air, one presence stood apart, not through sudden movement or display, but through scale that seemed to stretch beyond what the sky should allow. Quetzalcoatlus emerged as one of the largest known flying animals, its proportions extending into ranges that, even in comparison to its relatives, felt distant and unusual. Its wings, when fully extended, are estimated to have reached spans comparable to a small aircraft, forming a surface broad enough to interact with the air in a slow and measured way. This scale did not suggest constant motion, but rather a kind of deliberate stillness, where movement could be sustained with minimal visible effort. On the ground, its form carried a different kind of presence. When standing upright, Quetzalcoatlus is believed to have reached heights similar to that of a giraffe, its long neck rising above the surrounding landscape, supported by limbs adapted for both stability and motion. Its body did not appear built solely for flight, but for a dual existence, capable of navigating terrestrial spaces with coordination before returning to the air when conditions allowed. The proportions that defined it in flight were equally important in how it moved across the ground, creating a balance between two modes of life that remained closely connected. The structure of its skeleton reveals much about how such size could be supported. Its bones retained the same internal lightness seen in other pterosaurs, yet were reinforced in ways that allowed them to bear greater loads. The limbs, particularly the forelimbs, were robust, capable of generating the force needed to initiate movement upward. This suggests a launching method that relied on all four limbs, where the body could be propelled into the air through a coordinated push rather than a simple upward jump. Once airborne, the same extended wings that made takeoff possible would allow it to settle into a more energy efficient pattern of movement. Fossil remains, though incomplete, offer glimpses into this structure. Discovered in regions that were once part of ancient floodplains and inland environments, these fragments include elongated limb bones, vertebrae, and portions of the wing framework. Their scale alone provides evidence of the size these animals reached, while the arrangement of joints and surfaces suggests how they moved and supported themselves. Trackways attributed to similar large pterosaurs show impressions of both forelimbs and hind limbs, indicating a walking pattern that differed from that of birds, reinforcing the idea of a body adapted for life both above and below. Its skull, long and narrow, hints at a feeding strategy that did not require heavy force, but precision and reach. The absence of teeth in some specimens suggests a beak-like structure, suited for grasping rather than tearing, though the full range of its behavior remains inferred from limited evidence. What remains consistent is the sense that Quetzalcoatlus occupied a role shaped by its size, able to move across large areas and access resources that smaller animals could not. Within the broader progression of flight, this form represents a point where scale and function aligned in a way that extended the limits of what was possible. It was not simply larger than those that came before, but part of a system that had gradually adjusted to support such dimensions. Its presence reflects the culmination of earlier developments, carried forward into a form that balanced air and ground in a single, continuous design existing within a world that allowed such scale to persist. Lift did not depend on size alone, but on how force, balance, and timing came together in a single coordinated motion. For an animal as large as Quetzalcoatlus, leaving the ground required more than a simple upward movement. Its body was arranged in a way that allowed all four limbs to contribute, forming a system where the forelimbs played a central role in generating the initial thrust. The front limbs, longer and more powerful than those of most terrestrial animals, acted almost like loaded springs, storing energy as the body compressed downward before release. At the moment of launch, this stored force was directed into the ground through both the forelimbs and hind limbs, pushing the body upward and forward in a rapid extension. The motion was brief but precise, lifting the mass of the animal clear of the surface before gravity could pull it back. This quadrupedal launch created a stronger initial acceleration than would be possible with hind limbs alone, allowing even very large individuals to reach the necessary speed for their wings to begin interacting effectively with the air. Once airborne, the nature of movement shifted almost immediately. Continuous flapping, while possible, was not the primary method of staying aloft. Instead, the wings were positioned to capture rising air, allowing the animal to transition into a pattern of gliding and soaring. The large surface area of the wings provided ample lift, and when aligned correctly with upward moving currents, this lift could be sustained with minimal additional effort. The body settled into a posture that balanced forward motion with vertical support, reducing the need for repeated exertion. The air itself offered structures that could be used in this process. Warm surfaces below heated the air, causing it to rise in broad, slow-moving columns known as thermals. By entering these upward flows, large pterosaurs could gain altitude without flapping, circling gently within the rising air until reaching a height where forward gliding could resume. Along coastlines and over varied terrain, differences in temperature and surface shape created additional patterns of movement in the air, forming pathways that could be followed across long distances. With each adjustment, the wings responded to subtle changes in pressure and flow. Small shifts in angle altered the balance between lift and drag, allowing direction and speed to be controlled without abrupt movement. The body remained extended, with minimal interruption to the smooth passage of air over its surfaces. This approach reduced energy loss, allowing flight to be maintained over extended periods without the constant demand of active flapping. Energy efficiency became the defining feature of this system. By relying on environmental support and the inherent lift generated by large wings, these animals could travel far while conserving the energy needed for other aspects of life. Feeding, landing, and launching again all required bursts of effort, but the time spent in the air could be sustained with relative economy. This balance allowed large size to become an advantage rather than a limitation, as greater wingspans provided access to air currents that smaller forms could not use as effectively. Through this integration of anatomy and environment, flight at such scale became not only possible but practical. The air was not resisted, but engaged with, forming a continuous exchange between body and atmosphere that allowed even the largest of these creatures to move with a steadiness that matched the world around them. Sound did not always accompany motion above, and for much of the time, the sky carried presence without announcement. Once large pterosaurs settled into stable flight, their movement became defined less by effort and more by continuity, where the act of staying aloft required little visible exertion. Wings extended fully, holding their shape against the air, they could pass overhead without the repeated beats that often signal approach in smaller flyers. The absence of constant flapping reduced not only energy use, but also the subtle disturbances that might otherwise ripple downward. In this state, flight became a quiet passage rather than an active display. The broad surfaces of their wings allowed them to maintain lift through steady interaction with air currents, adjusting only when necessary. Small changes in angle or posture replaced large, rhythmic movements, and these adjustments occurred gradually, often too subtle to notice from below. The result was a form of motion that blended into the sky itself, where distance and height further softened any trace of presence. This ability to remain nearly silent extended their reach across vast areas. By relying on sustained gliding and the support of rising air, they could move from one region to another without frequent landings, covering distances that would otherwise require repeated bursts of energy. Their travel did not follow a straight, hurried line, but a series of gentle arcs and gradual descents, guided by the invisible structures within the atmosphere. In this way, the sky became not just a space to cross, but a medium that carried them forward with minimal interruption. For those on the ground, this mode of movement altered the nature of awareness. Without clear auditory signals, detection depended on other cues, many of which could be fleeting or easily missed. A shift in light, a brief dimming, or a change in the pattern of brightness across the surface might be the only indication that something had passed overhead. These moments were often brief, and without consistent repetition, they offered little time for preparation. The quiet nature of flight reduced the distance between presence and proximity, compressing the interval in which a response could occur. Modern soaring birds provide a partial reflection of this behavior, though on a different scale. Large birds, such as albatrosses or vultures, also rely on extended wings and minimal flapping, using wind patterns to remain airborne for long periods. Their movement, like that of ancient pterosaurs, often appears effortless, with long stretches of gliding interrupted only by occasional adjustments. Yet, even these birds, smaller in comparison, create subtle sounds as air moves across feathers or wings, shift position, traces that can sometimes be detected under the right conditions. In contrast, the membrane wings of pterosaurs interacted with the air in a smoother, more continuous way, lacking the layered structure that produces many of these sounds. This difference contributed to a quieter passage where motion remained largely contained within the flow of air itself. Combined with their height and scale, it allowed them to move across landscapes with a reduced acoustic presence, blending into the atmosphere in a manner that left little trace. Through this balance of structure and environment, silent movement became not an absence, but a feature of their flight, shaping how they existed above and how they were perceived below. The form of the head offers a quiet record of how these animals interacted with the world, revealing patterns of feeding without the need for direct observation. In large pterosaurs, such as Quetzalcoatlus, the skull extended forward into a long, narrow structure, tapering toward a pointed tip. This shape reduced weight while maintaining reach, allowing the head to move with precision at the end of a lengthy neck. The absence of heavy jaw musculature and, in some cases, the lack of teeth suggests that feeding did not rely on crushing or tearing with force, but on grasping, lifting, and swallowing. The beak itself, likely covered in a keratin sheath, would have provided a firm yet lightweight surface, capable of securing small prey without adding unnecessary mass. Its length allowed access to spaces that shorter jaws could not reach, whether along the ground, within shallow water, or among low vegetation. This design points toward a feeding strategy that emphasized efficiency and adaptability, where the act of obtaining food was integrated into both movement and environment. Across coastal regions, these animals may have walked along the edges of water, scanning for fish stranded in shallow areas or small creatures moving near the surface. The transition between land and water created zones rich in activity where prey was often concentrated and easier to approach. With long limbs and an elevated posture, they could move steadily across these areas, lowering the head when an opportunity presented itself. The beak would then act quickly, lifting the prey before it could escape, relying on timing rather than prolonged pursuit. Inland, similar patterns likely unfolded across open terrain and floodplain environments. Small vertebrates, including early mammals and juvenile reptiles, formed part of a landscape where movement was constant but often exposed. A large pterosaur moving across the ground would not need to chase with speed, but could rely on awareness and positioning, approaching slowly before extending its reach. The height of the body allowed a broader field of view, and the length of the neck extended that reach outward, reducing the need for sudden movement. Carrion may have also played a role in their diet. The ability to travel across wide areas would have allowed them to locate remains left by other predators or natural causes. In such cases, feeding would not require active hunting, but rather the ability to detect and access resources that were already available. The beak, suited for grasping, could lift pieces of soft tissue, and the relatively lightweight skull would allow repeated movement without excessive strain. This range of feeding behaviors reflects a pattern of opportunism, where diet was shaped not by a single specialization, but by the availability of resources within different environments. Rather than focusing on one type of prey, these animals likely adapted their behavior based on what could be found, shifting between coastal and inland settings as conditions changed. Their ability to move efficiently through the air supported this flexibility, allowing them to explore and exploit areas that were separated by distance. Within this framework, feeding became an extension of movement itself. The same structures that allowed flight also enabled access to a variety of food sources, linking aerial travel with terrestrial interaction. The result was a way of life that remained open to variation, guided by form and opportunity rather than restriction. From high above, the ground did not appear as a continuous surface, but as a shifting pattern of textures, where movement stood out against stillness in subtle but detectable ways. Large pterosaurs, carried by steady air, could observe wide areas without altering their position, their elevated perspective allowing them to track changes that would remain unnoticed at lower levels. Small motions, a brief adjustment in direction, or a disturbance among vegetation created signals that traveled upward, forming points of focus within an otherwise quiet landscape. This vantage allowed detection to occur at a distance, where approach could begin long before presence was sensed below. The body remained extended, wings held in a stable configuration as the animal adjusted its course through gradual shifts in angle. Rather than descending immediately, it could align itself with the movement it had observed, closing distance slowly while maintaining altitude. The transition from observation to action was not abrupt but measured, shaped by position and timing. When the moment came to descend, the change in movement was controlled but decisive, wings angled slightly inward, altering lift and allowing gravity to contribute to forward motion. The body inclined downward, converting height into speed, while maintaining enough control to adjust direction as needed. Air flowed more rapidly across the wing surfaces, and subtle corrections guided the path toward a specific point on the ground. This descent did not rely on sudden force, but on the steady increase of momentum directed with precision. As the distance narrowed, the long neck extended forward, bringing the head into alignment with the path of motion. The beak, narrow and elongated, became the primary point of contact, positioned to intercept the target at the exact moment of approach. Timing was essential, as the opportunity existed only within a brief interval where speed, angle, and position aligned. The strike itself was not prolonged, but quick, a single motion that relied on reach and accuracy rather than repeated effort. For animals below, the sequence unfolded within a compressed span of time. The approach, often silent, offered little indication until the final moments of descent, when changes in light or movement might become visible. By then, the interval available for response was limited, shaped by how quickly the signal could be recognized and translated into action. Escape depended on immediate reaction, often directed toward the nearest form of cover, though distance and timing did not always allow for successful avoidance. This interaction between height and ground created a dynamic where visibility did not guarantee safety. The ability to observe from above extended the reach of the predator, while the quiet nature of its movement reduced the cues available to those below. In this balance, hunting became less about sustained pursuit and more about positioning, where the advantage lay in the alignment of perception and motion. Across different environments, this method could be adapted to varying conditions. Open areas allowed clearer lines of sight, while regions with more structure required adjustments in approach and timing. In each case, the underlying process remained consistent, shaped by the ability to detect, align, and descend with precision. The air served not only as a pathway, but as a means of extending awareness, linking distant observation to immediate action through a continuous, controlled movement. Scale changed more than appearance. It altered how these animals interacted with distance, time, and the space around them. As wings extended and bodies followed, movement through the air became less about continuous effort and more about maintaining position within a system that already carried them forward. Larger forms could remain aloft with a steadiness that smaller bodies could not sustain, their broad wings engaging with air in a way that reduced the need for frequent correction. Each movement covered more ground, not through speed alone, but through efficiency, where energy was conserved across long intervals of travel. With this efficiency came reach. A single journey could extend across wide regions, linking distant environments without interruption. Where smaller animals might be limited by the need to rest or feed frequently, larger pterosaurs could move between areas with fewer stops, allowing them to access resources spread across greater distances. This ability to travel widely did not require constant searching, but rather a gradual exploration of the landscape from above, where movement itself became a method of observation. Height expanded this advantage further. From elevated positions, the surface below resolved into patterns that revealed activity across broad areas. Changes in texture, shifts in motion, and subtle contrasts in color provided information that could be interpreted from afar. This wider field of view allowed large flyers to identify opportunities without needing to approach closely at first, reducing unnecessary movement and allowing more precise alignment before descending. The sky, in this sense, became not only a pathway, but a vantage point that extended perception beyond the limits of the ground. As size increased, vulnerability decreased. Few animals within these environments possessed the means to challenge a fully grown pterosaur. Their ability to take to the air removed them from most forms of terrestrial risk, and their scale alone discouraged many potential threats. While younger individuals may have faced greater exposure, maturity brought a level of security that allowed these animals to move with less constraint. This relative absence of predation did not remove the need for awareness, but it shifted the balance, allowing energy to be directed more toward movement and feeding rather than constant avoidance. Over time, these combined advantages shaped their role within the environment. Larger pterosaurs occupied positions that connected distant parts of the landscape, influencing patterns of movement and interaction below. Their presence extended across coastlines, inland regions, and open terrain, integrating these areas through the paths they traced in the air. They were not confined to a single habitat, but moved between them, carrying with them the ability to exploit a range of opportunities. Dominance, in this context, did not arise through direct confrontation, but through the ability to operate across scales that others could not match. Size allowed access, efficiency allowed persistence, and perspective allowed awareness. Together, these traits formed a system in which large flyers could exist with a degree of continuity, their movement shaping the space around them without the need for constant exertion. Within this arrangement, being large was not simply a matter of scale, but a condition that aligned with the structure of the environment itself. The air supported them, distance became manageable, and the ground below unfolded in ways that could be read and approached with precision, reinforcing a presence that remained steady across time and space. Safety, for smaller animals, was not defined by strength or territory, but by how effectively they could remain unseen within a world that rarely offered complete concealment. Their bodies were shaped for survival under constant exposure, where protection depended on reducing visibility rather than resisting force. In environments where the sky carried presence without warning, defense became a matter of subtlety, guided by patterns that allowed them to blend into the surfaces they moved across. Coloration played a central role in this balance. Tones matched the surrounding ground, vegetation, or sediment, breaking up the outline of the body so that it dissolved into the textures around it. Stripes, modeling, and shifts in shading created irregular patterns that made recognition more difficult, especially when viewed from a distance. Stillness enhanced this effect, as remaining motionless allowed these patterns to merge fully with the environment, turning the animal into a continuation of what lay beneath it. Yet stillness could not be maintained indefinitely. Feeding, movement, and interaction required exposure, and each moment spent in the open carried a degree of risk. To manage this, many species relied on brief, controlled bursts of activity. Movement was kept short and direct, often following paths that led between areas of partial cover. These bursts of speed were not designed for long pursuit, but for rapid displacement, allowing the animal to cross vulnerable spaces quickly before returning to concealment. Speed itself was often limited by size and structure, making endurance less important than acceleration. Muscles were tuned for sudden release of energy, enabling quick starts that could create just enough distance to reach safety. Direction could change abruptly, with sharp turns that disrupted a direct line of approach. These movements introduced unpredictability, reducing the chance of interception during the critical moments of escape. Proximity to cover became an essential part of daily movement. Animals rarely strayed far from features that could provide even partial protection, whether it was a cluster of plants, uneven terrain, or narrow openings in the ground. These features did not always offer complete refuge, but they interrupted visibility and created barriers that could be used to break line of sight. The landscape was not simply a place to move across, but a map of possible retreats, where each step was influenced by the distance to the nearest form of concealment. In areas where cover was sparse, behavior adjusted accordingly. Activity might become more intermittent, with longer periods of observation between movements. Groups could form temporarily, increasing the chances that one individual would detect change early, though this also introduced additional motion that could be noticed from above. Each strategy carried its own balance, shaped by the conditions of the environment and the limitations of the body. Within this system, vulnerability was not constant, but fluctuated with position, timing, and awareness. Survival depended on maintaining a narrow margin where exposure was minimized and response remained immediate. There was no single defense that guaranteed safety, only a series of adaptations that worked together to reduce the likelihood of detection and allow escape when necessary. Across the ground, life persisted through these quiet adjustments, guided by an ongoing effort to remain part of the landscape rather than stand apart from it. Sight became the primary thread connecting ground and sky, a continuous stream of information that allowed small animals to interpret a world where change could arrive without sound. Vision was not simply a sense among others, but a system refined to detect the slightest variation across open space. The position of the eyes reflected this need, often set along the sides of the head to create a wide field of view. This arrangement reduced the area that could not be seen, extending awareness outward in nearly every direction, even if it limited the depth perception found in forward facing vision. With this broader perspective, the surface of the world could be monitored continuously. Movement, even when slight, stood out against the relative stillness of the surrounding environment. A shift in position, a disturbance in pattern, or a brief interruption in light created signals that could be recognized quickly. These signals did not require full understanding, only enough recognition to trigger a response. The connection between detection and action remained immediate, shaped by the need to react before proximity reduced the chance of escape. Light played a crucial role in this process. The position of the sun created contrast across the ground, forming areas of brightness and shadow that changed throughout the day. Within this shifting pattern, any alteration carried meaning. A moving shadow, even if brief, could indicate the passage of something above, its presence translated into a change in light rather than a visible form. Sensitivity to these variations allowed animals to respond to threats that were not directly seen, relying on indirect cues that traveled across the surface. The structure of the eye supported this sensitivity. Large pupils allowed more light to enter, improving detection under varying conditions, while specialized cells within the retina enhanced the ability to perceive motion. These adaptations did not provide detailed images at all distances, but prioritized the detection of change over clarity. The world, as experienced through this system, became a dynamic field where motion carried greater significance than fine detail. This reliance on vision extended into behavior. Heads remained in near constant motion, making small adjustments that refreshed the field of view and reduced blind spots. Blinking was brief and often timed with moments of reduced activity, minimizing the interruption of sight. Groups, when present, created overlapping fields of vision, where multiple perspectives increased the chance that change would be detected early. Each individual contributed to a shared awareness, though each remained responsible for its own response. Over time, these traits became more pronounced, shaped by the pressures of living under a sky that could not always be read directly. Eye placement, sensitivity to movement, and the interpretation of light all evolved together, forming a system that extended beyond the limits of any single sense. Vision became not just a way of seeing, but a method of anticipating, allowing animals to respond to events that had not yet fully arrived. Within this framework, Survival depended on maintaining this connection between sight and action. The ground remained open, the sky remained distant, and between them, vision carried the information that allowed life to continue within a narrow margin of awareness and response. Light traced the surface in a constant, shifting pattern, laying out a field of brightness that revealed even the smallest interruption. Across open ground, where cover remained limited and exposure was difficult to avoid, illumination became more than a backdrop. It formed a system of contrast that allowed change to stand out, turning movement above into something that could be read below, even when the source itself remained unseen. As the sun moved across the sky, it cast consistent angles of light that stretched shapes along the ground. Objects gained elongated forms, and even slight alterations in position produced noticeable differences in how that light fell. Within this steady arrangement, a passing body overhead introduced a disruption that did not belong to the surrounding pattern. The resulting shadow moved differently, its path crossing natural lines and textures in ways that could be recognized as separate from the environment. For small animals, this shifting darkness carried immediate significance. A moving shadow could appear without sound, its presence detected not through direct sight of the source, but through the effect it created on the surface below. The change was often brief, lasting only as long as the object above passed between the sun and the ground. Yet, within that short interval, the signal was clear enough to initiate a response shaped by patterns of behavior that had developed over long periods of exposure. Reactions to these signals were rapid and often automatic. The body responded before full interpretation, translating the visual cue into motion directed toward safety. This movement was typically short and decisive, aimed at reducing visibility or reaching the nearest form of cover. The response did not depend on identifying the exact source, only on recognizing that the change in light represented a potential threat. In this way, the shadow functioned as an early warning, providing a moment of awareness before direct proximity occurred. The effectiveness of this system relied on consistency. Sunlight created a stable baseline, where most shadows remained fixed or moved predictably with the position of the sun. Any deviation from this pattern became noticeable, allowing animals to distinguish between ordinary changes and those that required attention. Over time, sensitivity to these differences became more refined, with even subtle variations capable of triggering a reaction. Behavior adapted to reinforce this reliance on visual cues. Activity often aligned with conditions where light provided clear contrast, allowing shadows to be more easily detected. In areas where lighting was uneven or obscured, movement became more cautious, reflecting the reduced reliability of these signals. Groups, when present, could amplify detection, as multiple individuals increased the likelihood that a passing shadow would be noticed by at least one member. Across the ground, this interaction between light and movement formed a quiet exchange, linking events above to responses below without the need for direct contact. Shadows carried information that extended beyond the limits of sight, allowing detection to occur even when the source remained out of view. The landscape itself became a surface where these signals played out, shaped by the position of the sun and the movement of bodies passing overhead. Within this system, survival depended on recognizing and responding to these fleeting changes, where a brief shift in light could mark the difference between remaining unseen and becoming exposed. The boundary between open ground and dense growth formed a narrow band where conditions shifted in subtle but important ways. Along these edges, visibility softened without disappearing entirely, creating spaces where movement could be concealed while awareness remained partially intact. Forest margins, clusters of vegetation, and uneven terrain offered a kind of intermediate environment, neither fully exposed nor completely enclosed, where small animals could navigate with greater control over how much of themselves remained visible. Within these zones, the arrangement of plants and natural structures interrupted clear lines of sight. Stems, leaves, and irregular surfaces broke up outlines, allowing bodies to blend into layered textures rather than stand apart against open ground. Movement could occur in shorter, more controlled intervals, with each step passing through areas that provided partial concealment. The environment itself became a series of overlapping barriers, reducing the distance over which any single line of sight could extend uninterrupted. Burrows added another dimension to this system. Dug into soil or hidden beneath roots and debris, these spaces offered a level of protection that surface cover could not fully provide. Inside, temperature remained more stable, and exposure to external conditions was reduced. Entry points were often small and positioned carefully, allowing quick access while limiting visibility from outside. For many early mammals and smaller reptiles, these underground shelters formed the center of daily activity, with excursions above ground timed and measured against the surrounding conditions. Dense vegetation served a similar purpose, though with different limitations. Thick growth created a network of passages that could be navigated without fully emerging into open space. Within these areas, movement became slower and more deliberate, as the environment restricted speed but increased concealment. The density of the surroundings absorbed sound and disrupted clear visual signals, making detection more difficult. At the same time, this same density reduced outward visibility, narrowing the field of view and limiting the ability to monitor changes beyond immediate surroundings. This balance introduced a constant trade off. Remaining within cover reduced exposure, but also constrained awareness. Venturing into more open areas increased the ability to detect distant movement, yet removed the protective layers that concealed the body. Animals moved between these conditions with careful timing, often pausing at the edges to observe before crossing into more exposed ground. The decision to remain hidden or to move outward was shaped by immediate needs, such as feeding or relocation, weighed against the level of risk present in the environment. Paths formed along these boundaries, not as fixed routes, but as patterns of repeated movement where cover remained accessible at each step. These pathways allowed individuals to traverse larger areas without fully committing to open space, linking resources while maintaining proximity to shelter. The landscape, in this sense, became structured by these edges, where transitions between visibility and concealment defined how movement unfolded. Across these environments, living near cover did not eliminate exposure, but reduced its duration and intensity. Survival depended on maintaining access to these protective features, using them to interrupt visibility and create moments of concealment within a broader landscape that remained largely open. In this quiet negotiation between safety and awareness, the edges of the environment became as significant as the spaces they separated, shaping how life moved and persisted within them. Distance stretched outward without interruption, and in that openness, the ground offered little resistance to visibility. Across floodplains and coastal expanses, the terrain settled into broad, continuous surfaces where elevation changed slowly and features remained sparse. These environments formed where water once moved or still lingered, leaving behind flat layers of sediment that extended for great distances. Vegetation, when present, grew lower and more scattered, shaped by soil conditions and periodic flooding that limited the establishment of dense growth. Within these wide spaces, movement became more easily traced. Without vertical structures to interrupt sightlines, any shift in position carried across the surface with clarity, allowing it to be observed from far above. The ground did not conceal, but revealed, turning each motion into a signal that could travel upward without obstruction. This clarity was not constant, as weather and light altered how the surface appeared, yet the general absence of cover remained a defining feature. Floodplains, in particular, created conditions where activity unfolded across open ground shaped by the movement of water. Channels shifted over time, leaving behind patches of exposed sediment interspersed with areas of low vegetation. These regions supported a range of life, drawn by the availability of resources left behind by receding water. Yet the same openness that allowed access also increased exposure, creating an environment where presence was more easily detected from a distance. Along coastlines, a similar pattern emerged. The meeting of land and sea produced stretches of terrain where surfaces remained relatively level, influenced by tides and the gradual deposition of material. These areas often lacked the density of inland vegetation, forming transitional zones where movement could occur with few obstacles. The reflective quality of water nearby added another layer, as light shifted across the surface, altering contrast but not removing the overall openness. In such settings, the absence of cover changed how animals moved and behaved. Paths became more direct, as there were fewer features to navigate around, yet this directness increased visibility. Movement had to be carefully timed and often limited in duration, as prolonged activity in the open extended the window of exposure. Individuals might pause more frequently, scanning the surroundings before continuing, using brief intervals of stillness to reduce detection. The sky above these landscapes offered a clear vantage, unobstructed by the structures that might otherwise limit sight. Large flying animals could observe wide areas without needing to change position significantly, their perspective encompassing multiple points of activity at once. This advantage transformed open landscapes into areas where detection could occur earlier and more consistently, compressing the time available for response once movement was identified. Risk, in this context, did not arise from a single source, but from the interaction between visibility and movement. The ground provided access to resources, yet offered limited means of concealment, creating a balance where presence was both necessary and hazardous. Animals adapted by adjusting their behavior, relying on timing, speed, and awareness to navigate these conditions. Across floodplains and coastal regions, life persisted within this open arrangement, shaped by the constant negotiation between access and exposure. The landscape itself did not change quickly, but its influence on behavior remained immediate, guiding how movement unfolded across surfaces where distance carried information as clearly as it carried light. Air did not remain still, even when it appeared calm at the surface, and its movement shaped how life above and below unfolded from moment to moment. Invisible flows passed across the landscape, rising, sinking, and shifting in response to heat, terrain, and the presence of water. For large flying reptiles, these patterns formed pathways that could be followed with precision, allowing travel to extend far beyond what muscle alone could sustain. The sky, in this sense, carried structure, and those adapted to read it could move within it with quiet efficiency. Gentle currents often developed where the ground warmed under sustained sunlight, causing air to lift gradually upward. These rising columns created regions where lift increased without the need for continuous effort, supporting extended periods of flight. Large wings could settle into these flows, maintaining altitude while drifting slowly across the landscape. Movement became less about propulsion and more about alignment, where adjusting position within the current allowed progress to continue with minimal exertion. Over time, this interaction between body and atmosphere formed a reliable method of travel, linking distant areas through patterns that repeated with consistency. Wind also moved horizontally, carrying air across open regions in broad, steady streams. Along coastal margins and expansive plains, these flows followed predictable directions shaped by differences in temperature and pressure. By orienting themselves within these streams, large flyers could glide along with the movement, conserving energy while covering significant distances. The combination of upward and horizontal motion created a layered system where vertical lift and forward drift worked together to sustain flight over long intervals. Yet the same forces that supported movement could also disrupt it. Storm systems introduced rapid changes in air pressure, temperature, and direction, breaking the stability that sustained controlled flight. Strong gusts and turbulent currents altered the balance between lift and control, making precise movement more difficult to maintain. Under such conditions, the air no longer provided a steady surface to engage with, but became unpredictable, shifting too quickly to allow reliable navigation. During these periods, activity in the sky likely decreased. Large pterosaurs, dependent on stable air patterns, would have remained grounded until conditions returned to a more predictable state. The ground, though offering less freedom of movement, provided stability during times when the air became uncertain. This shift in activity altered the rhythm of life below, as the absence of overhead movement changed the balance of exposure and safety. Weather did not remain constant across all regions or times of day. Variations in temperature, cloud cover, and wind patterns created changing conditions that influenced when and where flight could occur. On days with clear skies and steady warming, air currents formed gradually, supporting extended movement above. In contrast, overcast conditions or shifting winds reduced the reliability of these currents, limiting how long and how far large flyers could remain airborne. For animals on the ground, these changes carried indirect effects. Periods of stable weather increased the presence of movement above, while unstable conditions reduced it, altering the level of exposure experienced at different times. Activity patterns adjusted in response, aligning with moments when risk was lower or higher, depending on the state of the atmosphere. Within this system, weather acted as a quiet regulator, shaping the interaction between sky and ground through patterns that repeated and varied over time. The air remained in motion, and within that motion, life found ways to move with it or wait for it to settle. Light divided the rhythm of this world into two distinct states, each shaping how movement unfolded across both sky and ground. During daylight, the surface was illuminated in full, revealing detail, contrast, and motion with clarity. The same conditions that allowed ground animals to see also enabled those above to navigate with precision, as visibility extended across wide distances without obstruction. In this brighter interval, activity in the air aligned with the presence of light, where flight depended on clear visual cues and the stable air patterns that formed under sustained warmth. Large pterosaurs were likely most active during these hours, their movement guided by both vision and the behavior of the atmosphere. As the sun warmed the surface, rising air currents developed gradually, creating supportive conditions that allowed extended periods of flight. These patterns did not form instantly, but built over time, reaching a consistency that could be relied upon. Within this window, large wings could engage with the air in a way that made travel efficient, allowing these animals to move across regions while maintaining control and stability. For those on the ground, daylight carried a different set of conditions. Visibility increased awareness, but also exposure, as movement became easier to detect from above. Activity during this time required careful adjustment, balancing the need to feed or relocate with the increased likelihood of being seen. Behavior often became more deliberate, with shorter movements and frequent pauses, reflecting the heightened connection between visibility and risk. The presence of light did not guarantee safety, but it provided the information needed to respond when change occurred. As daylight faded, the environment shifted into a different state. Light diminished gradually, softening the contrast that had defined the surface throughout the day. Details became less distinct, and movement was harder to detect at a distance. For large flying reptiles, these conditions reduced the effectiveness of visual navigation, limiting their ability to observe and align with targets below. Without clear visual cues, the precision required for controlled flight and hunting decreased, making sustained activity in the air less practical. On the ground, this transition altered the balance of exposure. Reduced visibility limited the distance over which movement could be seen, decreasing the likelihood of detection from above. Activity patterns adjusted in response, with some animals becoming more active as the cover of darkness provided a different form of protection. Movement could extend for longer periods, and the need for constant visual scanning softened as the environment itself concealed detail. This shift did not remove risk entirely, as other senses and behaviors continued to play a role, but it redistributed the conditions under which life operated. The absence of strong light reduced the dominance of visual detection, creating a temporary reprieve from the patterns that defined the day. In this quieter interval, the connection between sky and ground remained, but it functioned with less intensity. Across these alternating periods, behavior adapted to the changing qualities of light. Day and night formed a cycle that influenced when movement occurred, how far it extended, and how exposure was managed. The environment did not pause, but shifted continuously between these states, guiding life through patterns that repeated with each passing interval, shaping a rhythm that extended across the entire landscape. Above the surface, the air was not occupied by a single form, but shared among many, each moving within the same broad space while following slightly different patterns. Multiple pterosaur species existed at the same time, their presence overlapping across regions where conditions supported sustained flight. Though they shared the sky, they did not all use it in the same way. And within these differences, a structure emerged that allowed them to exist together without constant interference. Variation in size created one of the most important distinctions. Smaller species, with shorter wings and lighter bodies, moved with greater agility, adjusting direction more quickly and often remaining closer to specific areas where resources were concentrated. Larger forms, by contrast, extended their movement across wider distances, relying on efficiency and scale to access environments that lay farther apart. These differences in scale influenced not only how they traveled, but also how and where they fed. Feeding strategies diversified alongside these physical variations. Some species may have focused on coastal zones where interactions between land and water created concentrated opportunities. Others likely ranged inland, scanning broader areas for movement across open terrain. Differences in beak shape, neck length, and body proportions supported these varied approaches, allowing each group to interact with its surroundings in ways that reduced direct overlap with others. Altitude also contributed to this separation. While all occupied the sky, they did not necessarily remain at the same height. Larger individuals, capable of sustained soaring, could remain at higher elevations for extended periods, observing from a distance before descending when needed. Smaller forms, requiring more frequent flapping and shorter intervals of flight, may have operated closer to the ground, moving between points with more direct routes. This vertical distribution created layers within the air where different species occupied distinct zones. Timing further shaped these interactions. Activity patterns could shift depending on conditions, with some species more active during certain parts of the day when air currents or visibility favored their style of movement. These variations reduced simultaneous use of the same space, allowing different groups to operate with less direct competition. The sky remained shared, but its use was staggered across time as well as position. Through these combined differences, resources became distributed across multiple dimensions. Space, height, and timing all contributed to a system where overlap was minimized without requiring direct exclusion. Rather than competing constantly for the same opportunities, species adapted to specific roles that aligned with their physical traits and environmental preferences. This division allowed a range of forms to persist within the same general environment, each contributing to a broader structure of aerial life. The result was not a uniform occupation of the sky, but a layered and varied presence where multiple species coexisted through subtle distinctions in behavior and form. Movement above became a composition of different paths and patterns, each intersecting at times, yet often remaining separate. Within this arrangement, balance was maintained not through dominance by a single form, but through the distribution of roles that allowed many to share the same vast space. Feathers began to appear in forms that did not follow the same structure as the membrane wings that had long defined the sky. Among certain small theropod dinosaurs, changes in the forelimbs and body covering produced surfaces capable of interacting with the air in a new way. These early birds emerged gradually, their presence at first subtle, moving through the same environments already occupied by larger flying reptiles. Their bodies remained compact, their wings built from layered feathers that could be adjusted with fine control, allowing movements that differed in both scale and style. Their size shaped how they navigated the air. Smaller frames required more frequent motion to remain aloft, yet allowed for rapid changes in direction that larger forms could not easily achieve. Short bursts of flapping produced quick gains in altitude or speed, followed by brief glides that carried them between points of interest. This pattern created a form of flight that was more dynamic, with constant adjustments guiding their path through the air. Where larger flyers relied on steady currents and extended wings, these early birds engaged directly with the air through repeated motion, maintaining control through continuous interaction. As their forms diversified, different species began to explore a range of ecological roles. Some remained close to vegetation, moving between branches and dense growth, where their agility allowed them to navigate confined spaces. Others extended their activity into more open areas, using rapid flight to capture small prey or access scattered resources. The structure of their beaks, the length of their wings, and the arrangement of their feathers all contributed to how they interacted with their surroundings, creating variations in behavior that reduced direct overlap with larger aerial species. Their presence introduced a new layer to the sky, not through displacement, but through addition. Smaller size allowed them to occupy spaces that had remained less accessible, including areas closer to the ground or within complex environments where larger wings would be difficult to maneuver. This expansion of available niches supported their continued diversification as different forms adapted to specific conditions and opportunities within the landscape. Flight itself took on a broader range of expressions. Feathered wings allowed for precise control over lift and drag, with adjustments made through the position and orientation of individual feathers. This capability enabled more refined movements, including hovering for short intervals or rapid changes in direction during pursuit. The air, once dominated by steady, gliding motion, now also carried quick, shifting patterns of flight that unfolded at smaller scales. Despite these differences, early birds did not immediately replace the larger flying reptiles. Instead, they coexisted, each group operating within its own set of advantages. Larger pterosaurs continued to move across vast distances with efficiency, while birds occupied more localized spaces where agility and responsiveness provided benefits that scale alone could not offer. This coexistence created a more complex aerial environment where multiple forms of flight interacted without fully overlapping. Over time, the presence of these smaller, feathered flyers added variation to the sky, expanding the range of behaviors and roles that could be sustained. Their arrival marked a shift not in dominance, but in diversity, where flight became expressed through different structures and strategies, each shaped by the same underlying medium of air, yet carried out in distinct and evolving ways. A subtle shift began to take shape as feathered forms increased in number, not through sudden replacement, but through the gradual addition of new movement patterns that altered how the air was used. The sky, once dominated by broad, steady paths, began to fill with smaller, more frequent motions, each following its own rhythm. These changes did not remove what came before, but layered over it, introducing variations that influenced how resources were accessed and how space was shared. With the arrival of more agile flyers, competition for food began to extend into areas that had previously seen less overlap. Smaller birds, capable of rapid acceleration and tight maneuvering, could exploit resources that required precision rather than reach. They could enter spaces near vegetation, follow quick moving prey, and adjust their path in ways that allowed them to respond instantly to change. This flexibility brought them into contact with food sources that were also accessible to smaller pterosaurs, creating points of interaction where their different flight styles met. The contrast in movement became more pronounced as these interactions increased. Large pterosaurs continued to rely on extended wings and steady gliding, maintaining efficiency over long distances while scanning for opportunities below. Birds, by contrast, engaged the air more directly, using repeated wing beats to sustain flight and to adjust position continuously. Their wings, composed of layered feathers, allowed for precise control, enabling them to hover briefly, climb sharply, or shift direction within confined spaces. These differences did not simply reflect variation in form, but defined how each group interacted with the same environment. As these patterns persisted, the structure of aerial ecosystems began to change. The sky was no longer divided primarily by scale, but by style and function. Different forms of flight created distinct pathways through the air, each aligned with specific behaviors and needs. Smaller birds occupied niches that emphasized speed and maneuverability, while larger pterosaurs retained roles that depended on endurance and broad coverage. The result was a more complex system where multiple strategies coexisted and influenced one another over time. This gradual shift also affected how resources were distributed. Areas that once supported a single type of aerial activity now hosted multiple forms, each accessing food in slightly different ways. Overlapping ranges required adjustments in behavior as species adapted to the presence of others by refining their own strategies. Some may have shifted their preferred environments, while others adjusted their timing or methods of feeding, reducing direct competition while still sharing the same general space. The changes were not immediate nor uniform across all regions. In some areas, the presence of birds remained limited, while in others, their diversity increased more rapidly. This uneven distribution created a mosaic of conditions where the influence of these new flyers varied depending on local environments and available resources. Over time, however, the overall effect became more apparent as the balance between different forms of flight continued to evolve. Through this process, the sky transformed from a domain defined largely by a single approach to one shaped by multiple interacting systems. Movement became more varied, interactions more frequent, and the use of space more intricate. The air remained the same medium, yet the ways it was engaged expanded, creating an environment where different forms of flight could coexist while gradually reshaping the patterns that had once defined it. Weight placed a quiet boundary on what the air could support, and as bodies expanded, that boundary drew closer, shaping how large flyers moved and where they could remain effective. Scale offered advantages, yet it also introduced constraints that could not be ignored. Every increase in size required corresponding adjustments in structure and behavior, and beyond a certain point, the balance between lift and mass became more difficult to maintain. The wings, though broad and capable, had to generate enough support to counter not only the weight of the body, but also the forces encountered during motion through the air. This balance depended heavily on conditions that lay beyond the control of the animal itself. Air density, temperature, and the presence of rising currents all influenced how effectively lift could be sustained. In warm environments where air moved upward in steady flows, large wings could engage these currents with relative ease, maintaining altitude with minimal effort. In cooler or more stable air, where upward movement was reduced, the same wings required greater input to remain aloft, increasing the energy needed to sustain flight. Takeoff presented one of the most demanding moments within this system. Leaving the ground required not only strength, but precise coordination between limbs and timing. The body needed to reach a speed at which the wings could begin to generate sufficient lift, and this had to occur within a limited space. Under favorable conditions, with stable ground and supportive air, this process could unfold smoothly. The initial push from the limbs provided enough momentum to transition into controlled flight, where lift could take over and reduce further effort. When conditions shifted, this process became more difficult. Uneven terrain reduced the ability to generate a stable launch, while soft or unstable surfaces absorbed force that would otherwise contribute to upward movement. Strong or erratic winds disrupted the balance needed during the initial phase, making it harder to align the wings with the direction of airflow. In such situations, the margin for error narrowed and the energy required to achieve lift increased. These limitations influenced where and when large pterosaurs could operate most effectively. Open areas with firm ground and consistent air patterns provided the most reliable conditions for takeoff and sustained flight. In contrast, environments where these conditions were less predictable required greater caution, as failed attempts at launch could result in prolonged exposure on the ground. The dependence on external factors meant that movement was not entirely free, but guided by the state of the environment. Size, while advantageous in many respects, carried with it a reliance on these favorable conditions. The same wings that allowed for efficient travel over long distances also required space and stability to function properly during the critical moments of ascent. As bodies grew larger, the threshold for successful flight became more defined, shaped by the interplay between anatomy and atmosphere. Within this balance, the limits of giant flight emerged, not as a barrier, but as a set of conditions that needed to be met. The air could support remarkable scale, yet only within the boundaries set by physics and environment. Movement remained possible, but always in relation to the forces that allowed it, forming a system where size and limitation existed together, each defining the extent of the other. Stone holds quiet records of motion, preserving traces of bodies long after movement itself has faded. Within layers of sediment that have hardened over time, fragments of bone and impressions in the ground provide glimpses into how these animals lived, not as complete scenes, but as scattered details that, when placed together, begin to suggest patterns of behavior. Each fossil does not tell a full story, yet carries within it small indications of structure, use, and interaction with the surrounding world. The bones themselves reveal more than shape alone. Their internal composition, marked by hollow spaces and reinforced walls, reflects the balance between lightness and strength that supported life in the air. Surfaces where muscles once attached show subtle textures, ridges, and depressions that indicate how force was applied during movement. In some specimens, areas of repeated stress leave traces of wear, slight changes in thickness or density that suggest how certain motions were performed more frequently than others. These details, though small, point toward patterns of use, where specific parts of the body carried greater demand. Joints provide further insight into how movement was structured. The range of motion allowed by these connections, inferred from the shape and orientation of articulating surfaces, indicates how limbs could extend, rotate, or support weight. In large pterosaurs, the configuration of the forelimbs suggests a role not only in flight, but in supporting the body during contact with the ground. The alignment of bones within the wings and limbs reflects a system adapted for both stability and controlled motion, where forces were distributed in a way that allowed transition between different forms of movement. Beyond the bones, the ground itself preserves moments of contact. Trackways, formed when feet pressed into soft sediment that later hardened, capture sequences of steps taken across ancient surfaces. These impressions show the placement of limbs, the spacing between steps, and the direction of travel. In some cases, marks attributed to both forelimbs and hind limbs appear together, indicating a quadrupedal gait, where movement on land involved coordinated use of all four limbs. The depth and shape of these tracks suggest how weight was distributed, offering clues about posture and balance. The arrangement of these tracks across a surface provides additional context. Patterns of movement can be inferred from the spacing and orientation of impressions, revealing whether the animal moved steadily, paused, or changed direction. In certain areas, multiple trackways intersect, suggesting the presence of more than one individual, though without direct evidence of interaction. These traces do not capture behavior in its entirety, but they indicate how movement unfolded across the ground, complementing the structural information preserved in bone. Other fossilized remains, such as the positioning of skeletons or the environments in which they are found, add further layers of interpretation. Specimens discovered in former floodplains or coastal regions align with patterns of movement and feeding inferred from other evidence, reinforcing the connection between structure and habitat. The absence or presence of certain features, such as teeth or specific bone proportions, contributes to an understanding of how these animals may have interacted with their surroundings. Together, These fragments form a composite view where structure, motion, and environment intersect. Fossils do not recreate the living moment, but they retain enough detail to suggest how bodies moved, how forces were applied, and how life unfolded within the spaces they once occupied. Images formed from distance and imagination often simplify what was, in reality, far more complex. Flying reptiles are frequently pictured as creatures that remained in the air almost continuously, drifting above the ground without pause, yet their lives were not defined by constant flight. Movement through the sky was only one part of their existence, balanced by time spent on land, where feeding, resting, and interacting with the environment took place. Their bodies were built to support both conditions, and the ground remained an essential part of their daily rhythm. Evidence preserved in bone and trackways suggests that these animals moved across the surface with coordination, not as awkward visitors, but as creatures adapted to navigate both air and land. Their limbs supported their weight effectively, and their posture allowed them to walk with stability. Flight required preparation and suitable conditions, and once airborne, energy was managed carefully. Remaining in the air indefinitely would not have been efficient, and so periods of flight were likely interspersed with intervals on the ground, where energy could be conserved and other activities could occur. Another common interpretation places them alongside modern birds, imagining them as larger versions of familiar forms. This comparison, while convenient, overlooks the fundamental differences in how their bodies were structured and how they interacted with the air. Birds rely on feathers arranged along modified forelimbs, creating layered surfaces that generate lift through a combination of shape and motion. Flying reptiles, by contrast, used a membrane supported by an extended finger, forming a continuous surface that responded differently to airflow. This distinction shaped not only how they flew, but how they controlled movement and balanced forces. Their anatomy followed its own path, separate from that of birds, reflecting a distinct evolutionary solution to the challenge of flight. The distribution of weight, the arrangement of muscles, and the flexibility of their wing surfaces created a system that operated under different principles. Control was achieved through subtle adjustments in tension and angle, rather than the independent movement of feathers. Even their method of launching into the air differed, relying on coordinated use of all limbs rather than a primarily hind limb driven leap. These differences extended beyond flight into other aspects of their biology. The structure of their skulls, the absence or presence of teeth, and the proportions of their necks and limbs all contributed to ways of feeding and moving that did not align with modern analogs. Their bodies were not simply scaled versions of existing animals, but unique configurations shaped by conditions that no longer exist in the same form today. Understanding these distinctions allows a clearer view of how they lived. They were not creatures confined to a single mode of existence, nor were they direct equivalents of modern flyers. Instead, they occupied a position that combined multiple adaptations, each contributing to a way of life that balanced air and ground within a single system. The sky was a part of their environment, but not the entirety of it, and their design reflects this integration rather than specialization alone. By moving beyond simplified comparisons, a more accurate picture emerges, one that recognizes the distinct nature of these animals and the environments that shaped them, revealing a form of life that does not fit neatly into familiar categories, but stands as its own expression of movement and adaptation. Absence reshaped the sky as much as presence once did, and over time, what remained above became lighter, quieter, and far less imposing in scale. The immense forms that once traced slow paths across vast distances are no longer part of the atmosphere, leaving behind a space that appears open in a different way. Without bodies of that size moving overhead, the relationship between ground and sky shifted, altering how life below interacts with what lies above. Modern birds, though capable and diverse, generally occupy a smaller range of sizes. Even the largest among them do not approach the scale once reached by the greatest flying reptiles. Their wingspans, while impressive, remain within limits that allow for frequent flapping, agile movement, and more localized patterns of travel. This difference in scale changes how they are perceived from the ground, as their passage does not dominate the sky in the same extended manner. Movement above becomes more fragmented, composed of shorter flights and quicker transitions rather than long continuous glides. With this reduction in size, the nature of aerial presence becomes less overwhelming. Birds still hunt, still move across landscapes, and still interact with the ground below, yet the impact of their presence is distributed differently. Their approach often involves more direct motion, visible and audible in ways that provide clearer signals to those below. The intervals between detection and proximity are generally longer, allowing for more time to respond. This alters the balance of awareness, where cues become more accessible and less dependent on subtle changes. The absence of giant flying predators removes a layer of risk that once extended across wide areas. Large pterosaurs, capable of covering great distances with minimal effort, created a connection between distant parts of the landscape, allowing potential threats to appear from far beyond the immediate surroundings. Without such reach, modern aerial predators operate within more defined ranges, limiting the scale at which they influence ground behavior. Movement above remains present, but it does not carry the same expansive reach. This change influences how animals on the ground experience their environment. While vigilance remains important, the intensity and nature of that vigilance differ. Visual cues are clearer, responses can be more measured, and the likelihood of sudden, silent approach from extreme distances is reduced. The sky, though still active, becomes a less dominant source of immediate threat, allowing ground life to operate with slightly broader margins of safety. Environmental factors also contribute to this perception. Changes in ecosystems over time have altered the distribution of habitats, influencing where and how modern birds feed and move. Many species remain closely tied to specific environments, reducing the frequency with which they cross large, open areas in sustained flight. This further limits the extent of their influence across wide landscapes, reinforcing the sense of separation between ground and sky. Together, these differences create a shift in how the sky is experienced. It remains a space of movement, but its scale, patterns, and interactions no longer mirror those of the past. The absence of immense forms, combined with the presence of smaller, more localized flyers, reshapes the balance between visibility, distance, and response, leaving a sky that feels quieter not because it is empty, but because its nature has changed. A moment arrived when the patterns that had sustained this world began to break, not gradually as before, but through a sudden disruption that altered conditions across land, sea, and sky. Around 66 million years ago, an asteroid impact introduced a force large enough to shift the balance of entire systems. The event did not remain confined to a single location, but sent effects outward, changing the atmosphere and the flow of energy that supported life on a global scale. In the immediate aftermath, material thrown into the air spread across vast regions, forming a layer that reduced the amount of sunlight reaching the surface. Light, which had guided movement and supported plant growth, became limited, and with it, the processes that depended on it began to slow. Temperatures shifted, and the stability that had allowed predictable patterns of air and climate was disrupted. The environment did not settle quickly, but entered a period of uncertainty where familiar cycles no longer held. Plants, forming the base of many ecosystems, experienced significant decline as reduced light limited their ability to grow. This change extended upward through the system, affecting herbivores that relied on consistent vegetation and, in turn, the predators that depended on them. The connections that had linked different forms of life began to weaken, not through a single cause, but through a chain of dependencies that could no longer be maintained under altered conditions. For large flying reptiles, these changes presented challenges that extended beyond any single adaptation. Their reliance on stable air patterns, open environments, and accessible food sources meant that disruptions in climate and ecosystems affected multiple aspects of their survival simultaneously. With reduced sunlight, the formation of consistent rising air currents became less reliable, limiting the conditions that supported efficient flight. At the same time, the availability of prey shifted as populations of smaller animals declined or moved in response to changing environments. The scale that once provided advantages became more difficult to sustain under these new conditions. Larger bodies required consistent access to resources and suitable environments for both flight and movement on the ground. As these conditions became less predictable, the balance that had supported their existence began to falter. Energy demands remained, but the systems that supplied them no longer functioned in the same way. Across different regions, ecosystems moved toward collapse, not as an immediate disappearance of all life, but as a gradual breakdown of structure. Species that had once occupied stable roles found those roles altered or removed, and the interactions that had maintained balance became fragmented. Within this shifting landscape, the largest pterosaurs, already dependent on a narrow set of favorable conditions, faced increasing difficulty in maintaining their place. Over time, their presence diminished, leaving behind only the traces preserved in the geological record. The sky, once shaped by their movement, began to change as these forms disappeared. What followed was not an empty space, but a transformation, where other forms of life continued under new conditions, shaped by the same forces that had ended what came before. The end of the giant flyers did not occur in isolation, but as part of a broader transition that redefined the structure of life on Earth. The systems that had once supported their scale and movement gave way to new patterns, and within those changes, the sky became a different kind of space, no longer carrying the same forms that had once moved through it with quiet persistence. After the disruption had passed through air, water, and land, what remained was not an empty world, but one altered in its structure, where only certain forms could continue within the new conditions. Among those that persisted were birds, small feathered descendants of theropod dinosaurs, whose presence carried forward a lineage that had already begun to diversify before the event. Their survival was not the result of a single advantage, but of a combination of traits that aligned with the shifting environment. Smaller size played a central role in this persistence. Bodies that required less energy could endure periods where resources became limited or irregular. When plant life declined and food chains weakened, the ability to survive on smaller amounts of nourishment became critical. Birds, with their reduced mass and flexible diets, could adjust more readily to these changes, moving between food sources as availability shifted. Their mobility, supported by active flight, allowed them to relocate across regions in search of more stable conditions. The structure of their flight also contributed to this adaptability. Unlike large, soaring reptiles that depended on stable air patterns and wide open spaces, birds could sustain flight through continuous wing beats, allowing them to operate under a broader range of conditions. Even when the atmosphere became less predictable, their method of movement remained effective, enabling them to maintain access to different environments without relying on specific weather patterns. Reproductive strategies may have further supported their survival. Many birds laid eggs that developed relatively quickly, allowing populations to recover and adjust over shorter intervals. Nesting behaviors, often involving concealment or selection of protected sites, provided additional resilience in a world where exposure carried greater risk. These traits, combined with their size and mobility, created a system that could respond more rapidly to changing conditions. In contrast, large pterosaurs did not persist beyond this transition. Their scale, once an advantage, became a limitation when environmental stability declined. Larger bodies required consistent access to food and suitable conditions for both flight and movement on the ground. As ecosystems collapsed and resources became unevenly distributed, maintaining these requirements became increasingly difficult. Their reliance on specific air patterns for efficient flight further constrained their ability to adapt when atmospheric conditions shifted. The disappearance of these large flyers did not occur in isolation, but as part of a broader pattern where many large species across different environments were lost. Size, which had once allowed for dominance and efficiency, became more difficult to sustain when systems no longer supported continuous access to resources. Smaller organisms, with lower demands and greater flexibility, were better suited to endure the uncertainty that followed. What remained was a reshaped aerial environment, where birds carried forward the capacity for flight, though expressed in a different form. The sky did not lose movement, but its nature changed, reflecting the traits of those that survived. The absence of large pterosaurs marked the end of one system, while the persistence of birds allowed another to continue, adapted to a world that had shifted beyond the conditions that once supported greater scale. Within this transition, survival was not determined by strength alone, but by alignment with a changing environment where flexibility, efficiency, and scale together shaped what could endure. Traces of their presence remain not only in stone, but in the patterns that continued after they were gone. Subtle influences carried forward through the behavior and structure of life that followed. The ancient sky, once shaped by large, efficient flyers, left behind more than absence. It altered how ecosystems were organized, how movement was perceived, and how survival strategies developed across generations that never encountered those forms directly. While they existed, these flying reptiles connected distant parts of the environment, moving between regions that would otherwise remain separate. This ability influenced the distribution of life below, as predation, scavenging, and movement linked areas across wide distances. Their presence created pressures that extended beyond immediate interaction, shaping how species adapted to visibility, timing, and exposure. Even after their disappearance, the effects of these pressures remained embedded in the behaviors that had developed in response. On the ground, many of the traits that supported survival under aerial observation did not vanish. Wide fields of vision, sensitivity to movement, and rapid response patterns persisted, carried forward as part of a broader system of awareness. These adaptations, once shaped by the need to detect large, silent forms above, continued to provide advantages in environments where visibility still played a role. The influence of the sky became part of the internal structure of behavior, no longer tied to a specific threat, but maintained as a general strategy for survival. The development of flight itself also reflects this legacy. While birds follow a different structural path, Their continued presence in the air represents an extension of the space, first fully occupied by pterosaurs. The sky, once established as a viable domain for large vertebrates, remained available for new forms to explore. Though the scale and style of flight changed, the concept of sustained aerial movement persisted, carried forward into systems that operate under different constraints. Ecosystems adapted to this transition, reorganizing around the forms that remained. The absence of large aerial predators altered the distribution of risk, changing how animals moved and where they spent time. Yet the memory of earlier conditions, preserved through inherited behavior, continued to influence these patterns. Movement remained cautious in open spaces, and sensitivity to overhead change did not disappear entirely, even as the intensity of that threat declined. In this way, the ancient sky left a lasting imprint that extends beyond the organisms themselves. It shaped interactions between visibility and movement, influenced the development of sensory systems, and contributed to the diversity of flight that followed. These effects are not always visible as direct connections, but they persist in the structures and behaviors that define modern ecosystems. What once moved above has been replaced, yet the systems it helped form continue to operate, adapted to new conditions, but carrying traces of what came before. The sky no longer holds the same forms, but it remains part of a larger story, one that extends across time through the quiet continuity of life adjusting, responding, and evolving within the spaces it inhabits. There is a stillness to the sky now that feels familiar, a wide openness that stretches without interruption, where movement passes in brief intervals and then fades again into distance. It appears calm in a way that suggests space rather than presence, as though nothing substantial occupies it for long. Light moves across it without obstruction, and what crosses that space does so in smaller, more fleeting forms, leaving behind no lasting impression once it has passed. Yet this same expanse once held a different rhythm, one shaped by bodies that moved with sustained purpose across great distances. The air carried weight then, not in density, but in the scale of life it supported. Motion above was not occasional, but continuous, tracing slow paths that connected far horizons. What seems empty now was once structured by presence, where the sky itself formed part of the environment in which life unfolded. On the ground, this presence influenced how existence was lived from moment to moment. Movement was measured not only by what lay ahead, but by what might pass overhead without sound. Survival extended into a vertical awareness, where the space above became as relevant as the terrain below. Patterns of behavior formed around this condition, shaping how animals paused, moved, and positioned themselves within their surroundings. These patterns did not arise from a single interaction, but from repeated exposure across generations, where consistent pressures guided gradual change. Bodies and senses adapted to detect subtle variations, small shifts in light or motion that signaled a change in the environment. The sky was not separate from daily life, but integrated into it, influencing decisions that unfolded continuously across time. That world no longer exists in its original form. The large shapes that once defined the upper space are absent, and with them, the particular conditions that shaped those patterns of awareness. What remains is a quieter system where the connection between ground and sky is still present, but less dominant in its influence. Movement above continues, though it no longer carries the same scale or reach. Even so, the record of that earlier world persists, not in motion, but in the structures that endured. Stone holds the outlines of bodies and the marks of movement, preserving fragments that suggest how life once operated within those conditions. These traces do not recreate the experience, but they offer a way to understand how different the environment once was and how deeply it shaped the forms that lived within it. The sky today offers space, light, and distance, yet it also carries the absence of what once moved through it. That absence becomes part of the story, a contrast that reveals how conditions have changed over time. Life continues to adapt within the present, shaped by forces that differ from those that came before, yet still connected through a continuous thread of response and adjustment. As this passage settles, the sense of that earlier sky lingers quietly within the imagination, not as a return to what was, but as an awareness of how the world can transform. The openness above remains, steady and unbroken, while the memory of movement persists in the patterns left behind, held gently within the record of the earth itself.